All right, let's get ready for what is basically one of the greatest intellectual showdowns in all of science. In one corner, you've got Sir Isaac Newton, the absolute giant of classical physics. And in the other corner, Albert Einstein, the revolutionary who completely redrew our map of reality. And their battleground? Well, it's only the very nature of gravity itself.
So here it is, the central question, the one that splits two entire worldviews. Is gravity some kind of invisible rope that's pulling you down to Earth? Or are you simply sliding along a curve in the actual fabric of the universe? I'm telling you, the answer to that question changes absolutely everything.
You know, to really get why they disagreed so profoundly on gravity, we first have to wrap our heads around how differently they pictured the entire cosmos. It's a fundamental split right down to their imagination. And this metaphor really says it all. For Newton, space and time were like a rigid stage. They were absolute, unchanging, just a fixed backdrop for the predictable play of physics. But Einstein, he imagined a flexible fabric, a dynamic universe that could be bent, stretched, and warped by the very things moving through it.
Okay, let's start with the theory that dominated science for like over 200 years. Newton gave us this powerful, elegant, and incredibly useful picture of gravity. But as we're about to see, it had one tiny, reality-breaking flaw.
So for Newton, gravity was simple. It's a force, an invisible, instantaneous pull. Every object that has mass pulls on every other object that has mass. The Earth pulls on you, the Sun pulls on the Earth. It's this immediate connection right across empty space.
And this formula? It was completely revolutionary. It basically shows that the force of gravity depends on the mass of two objects and the distance between them. The more mass, the stronger the pull, the more distance, the weaker it gets. And look, it works perfectly for launching rockets and predicting tides. But
here's the fatal flaw. Newton's math demands that this pull is instantaneous. So think about it. If the sun were to just poof, vanish, his formula says the Earth would instantly fly off its orbit. But wait a minute. We know nothing can travel faster than light, not even information. So how could the Earth possibly know the sun was gone before that last bit of sunlight finished its 8-minute trip to reach us? It just doesn't add up.
And this is where Einstein enters the picture and just flips the whole table over. He proposed something so radical it honestly sounds like science fiction. He said, what if gravity isn't a force at all? What if it's just the shape of the universe?
Einstein's big idea is that mass doesn't create a pull, it creates a dent. You've probably heard this analogy, it's a great one. Imagine placing a heavy bowling ball on a trampoline. It curves the fabric around it, right? Well, if you roll a marble nearby, it doesn't get pulled by the bowling ball. It simply follows the curve that the bowling ball made. That's gravity. It's just geometry.
now, don't be intimidated by this equation. I know it looks like a beast. Let's just focus on the story it tells. On one side, you've got mass and energy. On the other side, you've got the geometry of space-time. So in plain English, it's saying mass tells space-time how to curve, and that curved space-time tells mass how to move. It's this beautiful cosmic dance.
So let's boil it all down. Newton looks at a planet orbiting the sun and says, see, an invisible force is pulling it off its straight path. But Einstein looks at the exact same planet and says, nope, the planet is going in a straight line. It's just taking the straightest possible path through a part of space that's been curved by the sun's mass. It's a profound shift from a pull to a path.
Okay, so we have two competing theories. How do we know who's right? Well, you got to look at the extreme cases, the places where Newton's simple math starts to fray at the edges and where Einstein's predictions are put to the ultimate test.
This right here perfectly captures the three key battlegrounds. For Newton, gravity is instant, light is totally unaffected by it, and time is just some absolute cosmic clock that ticks the same everywhere. But for Einstein, gravity travels at the speed of light. It actually bends the path of light, and get this, it can even slow down time itself. So this solves Newton's instant action problem right away. If the sun vanished, the gravitational wave, that ripple in space-time, would travel to us at the speed of light. We wouldn't feel the change for about 8.5 minutes. The darkness and the loss of gravity would arrive at the exact same time.
Now this was a truly wild prediction. Newton said gravity only affects things with mass, so light shouldn't care. But Einstein argued that light has to travel through space-time. So, if space-time is curved around a massive star, the light's path has to curve too. And this phenomenon, called gravitational lensing, was famously proven during a solar eclipse in 1919. It's the moment that made Einstein a global superstar.
And here's where it gets really bizarre.
For Einstein, time isn't separate from space. It's a dimension woven into what we call space-time. And just like space, it can be warped. The stronger the gravity, the slower time ticks. And this isn't just a theory. The GPS satellites orbiting Earth have to constantly correct their clocks because time for them is ticking just a little bit faster than it is for us down here on the ground.
But the rabbit hole goes even deeper. The split between Newton and Einstein goes beyond just gravity. It goes right to the very definition of what stuff even is. And this is where we run into the most famous equation in all of science.
Yep, we've all seen it. But what does it really mean? It means energy has mass, and mass is a form of energy. They're just two sides of the same cosmic coin. This idea completely shatters the classical Newtonian worldview.
Newton thought of mass as fundamental, indestructible stuff. An atom was an atom, period. But Einstein showed that mass is really just energy, all bundled up and contained. It's not passive, it's this huge reservoir of potential, and that potential is what gives it weight and allows it to warp space-time. Let's make this tangible. A proton is made of smaller particles called quarks, but if you add up their individual masses, it comes out to almost nothing. So where does the proton's mass come from? It comes from the colossal energy of the force that's binding those quarks together. That energy is the mass. And that means if you add energy to a particle, you literally make it heavier. And, none of Einstein's revolution would have been possible without the right mathematical tools. Newton used the geometry we all learn in school, Euclidean geometry, the math of flat surfaces and straight lines. But Einstein realized the universe wasn't flat. He needed a whole new language, and he found it in the work of a guy named Bernard Riemann, who had developed the mathematics for curved, multidimensional spaces.
And this is the ultimate takeaway. The shift from Newton to Einstein wasn't just a new formula for gravity. It was a complete transformation of our cosmic perspective. The universe was no longer some cold clockwork machine. It became a living, breathing, dynamic entity, constantly interacting with itself.
So let's end with this one last thought. We talked about how time slows down near heavy objects. Well, the Earth is a pretty heavy object. This means, and it has actually been measured, that time ticks just a tiny, tiny bit slower for your feet than it does for your head, because your feet are closer to the Earth's center of gravity. So what does it mean to live your entire life with your head aging just a fraction of a second faster than your feet? That is the strange and beautiful reality Einstein gave us.